Hi guys, it's your science teacher here back with another video. This time I'm going to go through the whole unit of chemical changes. So without further ado, let's get started with today's video. The topic of chemical changes starts off by looking at the reactivity of metals, and there's ways that we can work out the reactivity of metals. I can either add them into an acid or I can add them into water. Now, depending how vigorous my reaction is will help me identify which metal I have. So if I add an acid and I've got these first two metals, these are the most reactive. I have my reactivity going up here. So the most reactive are at the top and the least reactive are at the bottom. So what would happen if I added an acid to these top two, potassium or sodium? Well, I would most likely get an explosion. The reaction would be incredibly vigorous and very exothermic, meaning it gives out a lot of heat. So these top two, I will not add an acid to them just in case I get an explosion. You're almost creating a little bit of a mini bomb there. What about these next two, calcium, magnesium, and I can even include aluminium in this. I would get a vigorous reaction if I was to add these to an acid. And then what about these next ones, these carbon, zinc, iron? I would get a slow reaction with an acid. And then getting into the bottom, I would get no reaction when I get too low in my reactivity series. So silver and gold, even with quite a strong acid, you ain't going to get much of a reaction at all happening. So for them really reactive metals, it's probably better if I add water to try and help identify them. I'm going to get a vigorous reaction if I add them in. I'm going to get slower reactions with my next metals, and anything really past iron, you aren't going to visibly able to see a reaction taking place. I always think it's important to remember as well that you are not given this reactivity series in your exam. You might be given a bit of the reactivity series in the foundation paper, but you're expected to remember that certain metals are more reactive than other metals. So these are all qualitative ways of working out which one's more reactive by just looking at reactions. But you could quantitatively find out which one is more reactive. But for this experiment, you're going to have to control things a little bit better. And there are two ways you could either find out the reactivity. One is by looking at the increase in temperature. It's going to be an exothermic reaction when you add these metals to either an acid or water. Now, the key thing is thinking about what you're going to have to control in this practical. Your control variables are going to be really important. So what are you going to need to keep the same in order to have a fair test? Well, you're going to need to keep the same the mass of metal that you add each time. You're also going to need to control the amount of acid and also the starting temperature of that acid as well. So the increase in temperature is what you're going to measure in this practical. That would be my dependent variable. And you could use a thermometer to measure the starting temperature of your acid and your end temperature, and that would mean that my independent variable, the thing you're changing each time, would be the type of metal. I always think in a exam, if you get asked to plan a practical, always think about what your variables are before you get started. Another way to quantitatively work out which one is more reactive is you can count the number of bubbles given off when you add the acid to your metal, or it doesn't have to be acid, it could be water, remember, but remember with water not all of them do react with water, so it might be hard to identify them really unreactive metals using water. So what would I have to keep the same with this one? Well, I'm going to have to keep the time the same, aren't I? I'm going to have to always use the same amount of time, like count the bubbles in 3 minutes or something like that. I'm also going to have to keep the same as well, my mass of metal, just like last time, and my volume of acid. And remember this time that my count in the bubbles, this will be my dependent variable. This is what I'm going to measure. And obviously, the more bubbles that you get, the more reactive the metal will be. And the independent variable, the thing we're going to change each time, that will be the type of metal as well. And you could use a test tube rack with test tubes in, just like I've got set up over here. You could use test tubes and add them all in, 2 test tubes, and count them all next to each other. That would work as well. Now I know about the reactivity of metals and how to work out the reactivity of metals, I can start looking at what's called displacement reactions. And a displacement reaction happens when I have a more reactive metal which will displace a less reactive metal from the compound that it's in. I always explain to my class this is a little bit like Love Island. Everything likes to be coupled up in Love Island, and it's very similar with these metals. They like to be bonded to something else. And in Love Island, people come into the villa like bombshells, and they will displace people from the couples. And it's exactly the same with these metals. They will come in if they're more reactive and displace the less reactive metal from its compound. So let's have a look at an example of what I mean here then. So let's have iron, and I'm going to have iron bonded to bromine, which would be iron bromide. And if I add it to a more reactive metal, for example, something like magnesium, well, magnesium is more reactive, so it's going to steal that bromine away. And now I end up with magnesium bromide, and I have iron. Now, how can I tell whether I've had a displacement reaction? Well, things that we're going to look out for in this reaction is we're going to make a solid precipitate of the metal. When that metal has been made, it's going to come out of solution. So if you were making iron, you're going to see a solid precipitate that is going to be silver in colour. And you also might get a change in colour of a solution. So these are the things that you're going to be looking out for if you have a displacement reaction. Let's just have a look at another example here. So if I've got something like potassium, which is the most reactive of all the metals, and it's bonded to sulfate here. So I've got potassium sulfate as my salt solution, and I add in something like copper. Well, what's going to happen here? Well, this time I have my more reactive metal already bonded. So copper, in fact, cannot displace potassium from its bond with sulfate. So we will get no reaction taking place. Another name for displacement reactions is redox reactions, because one species is reduced and one species is oxidized. Now you can remember this way round by remembering oil rig, which is a mnemonic. It stands for oxidation is loss of electrons and reduction is gain of electrons. So let's have a look at one of them displacement reactions again. So this time I will choose, I'm going to choose calcium, and it's going to be bonded to iodine. So I have calcium iodide, which is CaI2. And I'm going to react it with some, this time I'm going to use sodium. Now, sodium is more reactive than iodine, so it will kick it out. So I'm going to end up with sodium iodide, and now my calcium is unbonded. Just to balance the equation and make everything look nice again, just remember to put 2 in front of my sodium there. Anyone thinking, why have I got 2 iodines over here? Remember, calcium is in group 2, so it's going to have an oxidation state of 2+. Iodine's in group 7, so it's going to be -1. So you need 2 iodines for every 1 calcium. So let's have a look at this redox reaction in a bit more detail then. So what is actually going on in this displacement reaction? Well, it's easier to understand if I have a look at the ions involved. So what I'm going to do down here is just draw out every single ion that I have in my reaction. So calcium, like I said, was calcium 2+ because it's in group 2. And iodine is 1-, and I've got 2 of them. And because my sodium is unbonded, it's going to have an oxidation state of 0. Anything unbonded has an oxidation state of 0. And it's going to 2Na, and now it's bonded to my iodine. And remember, sodium's in group 1, so it has an oxidation state of +1. I still have my 2I 1-, and now my calcium is unbonded. It's going to have an oxidation state of 0. So, what has actually gone on in this reaction? Well, if I get rid of what's called my spectator ions, ions that don't change oxidation state, my iodine here is staying at 1-. So that's called a spectator ion because it's not involved really in the reaction. It's what's being stolen, isn't it? It's easier to see if I get rid of it. And this is called an ionic equation. This is what's going on with my ions and oxidation states, anything that changes. So now I've seen that, I can see that calcium's gone from a 2+ ion into having 0 oxidation state. And if I split it up into half equations, I can actually see what has gone on. For calcium to have gone from 2+ to having an oxidation state of 0, what must have happened? Well, it must have gained 2 electrons. Just think of a calcium ion. If it's a calcium ion, it's going to be 2+. The reason is because of the fact it had lost 2 electrons. To go back from being an ion to the atom here, which is unbonded, it has to gain the 2 electrons that it must have lost. And then let's have a look at the sodium then. So it's going from 2Na having an oxidation state of 0 to 2Na plus 1. So what's gone on here? Well, it must have lost 2 electrons. Well, each sodium must have lost 1 electron for this to have happened. Just think of sodium, it's in group 1, so it has 1 electron in its outer shell, and it's getting rid of it to become a sodium ion, just like that. So let's talk about these in terms of oxidation and reduction. Well, if I look at calcium, it's gained electrons, so this one must be reduction. And what's happened with my sodium? Well, it's lost electrons, so my sodium has become oxidized. So in summary, I can think of these displacement reactions and the reactivity of metals. The more reactive a metal it is, the easier it oxidizes, the easier it loses electrons. And these reactions are called redox because one species is reduced, like the calcium was here, and one species is oxidized, just like the sodium was here as well. Now, you might have been wondering why carbon and hydrogen were included in the reactivity series that you saw earlier when I said this was all about metals and their reactivity. And the reason why I include carbon and hydrogen is because they're used in extracting metals. Now, metals are often extracted from what is called ores, and an ore is just a rock that contains a metal. So let's look at an example of one of these metals that I could extract from its ore in order to collect it using either carbon or hydrogen. So let's first have a look at iron. Now, iron can be extracted from its ore, which is often called iron oxide, using carbon. Now, if we look at the reactivity series over here, carbon is higher in the reactivity series than iron. As a consequence, the carbon will displace the iron from its oxide, and I will end up with carbon now bonded to the oxygen called carbon dioxide, and I will also end up with the iron that I want. Now, extracting a metal from its ore using this process, which is called smelting, involves quite a large amount of heat because you have to heat it to a high temperature, and also you create carbon dioxide gas, which, if you remember, this is a greenhouse gas, which obviously is not great for the environment. However, smelting is one of the most important industrial reactions that we have. We turn millions and millions of tons of iron oxide into iron using this process so that we can then form steel, which is an alloy out of iron. So preferably what I would like to do instead of using carbon is using hydrogen. So let's have a look at an example of where I could use hydrogen to extract. If I look at lead, lead is less reactive than hydrogen, so I could extract that with hydrogen, and this time my products of the reaction would be water, because the hydrogen would displace the lead, making hydrogen bonded to oxygen, which we know is water, and I would also make lead. It's also important to remember that these really unreactive metals found at the bottom of my reactivity series, they are often found pure. Because they are so unreactive, they do not really react with elements found in the atmosphere like water or oxygen, so they're often found pure, and I don't need to do any extracting with carbon or hydrogen. As well as knowing about displacement reactions and how to extract metals, we also need to know about some other key reactions involving acids. So if I just have a metal and I add an acid, I will always make the two same products. I will make myself a salt, and I will always make hydrogen as well. When I have a metal hydroxide and an acid, I will make salt, and I will make water. And when I have a metal carbonate and an acid, I'll make salt, water, and carbon dioxide. But how do I name these salts? Well, it depends what acid that I use in my reaction. Depending on the acid depends on the salt that you will make. So let's have a look at some of the names of these salts that I'll make. So if I use hydrochloric acid, I will make myself a chloride salt. And hydrochloric acid is HCl, and the salt ion for chloride is Cl1-. For sulfuric acid, I'll make myself sulfate salts, and the sulfuric acid is H2SO4, and the sulfate ion is SO4 2-. Nitric acid, I will make myself nitrate salts. And nitric acid has the formula HNO3, with the nitrate ion being NO3 1-. And then I have phosphoric acid, which makes phosphate salts. phosphoric acid is H3PO4, and the phosphate ion is PO4, 3 minus. So let's actually have a look at some of these in practice then. So let's say, for example, I have the metal calcium and I'm reacting it with hydrochloric acid. I will make, my salt will be called calcium chloride, and I will also make hydrogen as my other product. Remember, if you're doing the balanced symbol equation, you'll need to know which ions that you have in there. So this would be CaCl2 would be my formula of the salt that was made. Moving on to the next one, if I have a metal hydroxide and an acid, so this time I will switch up my metal and I'll switch up my acid as well. So for example, this time if I had magnesium and I was to react it with sulfuric acid, then my product, sometimes you see sulfuric acid with an F or a pH, it doesn't matter which one you do in your exam, really. I use the American spelling here just in case you ever see it written with an F. And the salt that will be made here is magnesium sulfate, and you'll also make water. And remember that sulfate is SO4 2 minus, and magnesium's in group 2, so this would just be MgSO4 for my salt. Moving on to looking at what my metal carbonate and acid would do, so I'll switch up my metal one more time. This time I'll use a group 1 one, so let's pick potassium carbonate. And this time I'm going to react it with nitric acid. And the products of this reaction would be potassium nitrate as my salt. I'm going to make water, and I'm going to make carbon dioxide as my other product as well. Now, another term that you will maybe hear for metal hydroxides and metal carbonates is base, because these are substances that can neutralize an acid. Basically, they react with the H plus ions, you make water as a byproduct, so you start off with an acid and you make a neutral solution at the end of it. And some of these bases can also be called alkalis, and an alkali is just any base that is soluble in water. Sometimes you might want to isolate the salt that you made in one of the reactions that we just looked at on the last slide, and there's ways of doing it. And first things first, you have to carry out your reaction. Now, there are different ways of carrying out the reaction. For example, sometimes you might want to heat or stir to make sure that the reaction has enough energy. You'll learn about in later topics, some reactions require what's called activation energy, a bit of energy to spark off that reaction. It's really important in this stage that we add our metal or metal hydroxide or metal carbonate in excess. The reason why it's important that we add it in excess is to make sure that all of my acid has reacted with that metal or metal carbonate or metal hydroxide. So when I get to the stage of further on, I'm not heating up acid and it's vaporizing in the air, and it might not be too nice to breathe in. You might have an indication that your reaction has finished. For example, you might see some solid being left in the bottom, and because that we've added our metal or metal carbonate or metal hydroxide in excess, I need to get rid of the extra solid that's going to be in there. So my next stage is I filter, and this gets rid of all of the unreacted solid This means when I do my later stages, I'm not collecting any of that solid that I started with. And what we call the useful product from a filter is my filtrate, so that will contain my salt and some water, and the bit left over, all of that excess, we call that our residue. The next stage is, after I've filtered to get rid of all my unreacted solid, I need to heat to evaporate any water or any of unreacted acid. There shouldn't be any left, but it would get rid of it. But remember, in these reactions, when I've got metal hydroxide or I've got myself a metal carbonate, I'm going to make some water as well. So we're going to heat it to evaporate that water off. You don't want to heat it the whole way. You want to heat it until about half of the water has gone. The reason why you heat it until just about half the water is gone, the reason for that is you can maybe lose some of your product if you heat any more. And then finally, what you're going to do is you're going to leave to crystallize, and you're going to dry them crystals. Now, to dry them crystals, you're going to want to think of somewhere warm. Maybe when you did this, you left them on the windowsill, or your teacher might have put them into an oven to dry them off, and all of these are good ideas. Now we're just going to go into a bit more detail on acids, what they actually are, and having a look at the pH scale. So the first thing to look at is this pH scale over here, and a pH scale is a measure of how acidic or how basic something is. So if I have a look at this pH scale, and we'll go start in the middle, 7 is right in the middle. It goes from 1 to 14, and 7 is what we call neutral, where it's neither acidic or basic. And as we go lower numbers in the pH scale, we start off with our weak acids, and then we have our strong acids right at the top, with the lowest pH of them all. And then going the other way, my larger numbers, they tell me if a substance is a base. So here we have a weak base with pHs of 9, 10, 11, and then we've got the really strong bases down here with pHs of 13 to 14. Now, next to them, they've got colours, and these are the colours that we would expect universal indicators to turn in the presence of the acid base, or whether it be neutral. And in an exam, you might get asked to predict what colour that an acid or a base would turn if it was placed inside one of these pH substances. Now we know what the pH scale is, we can investigate actually what an acid is. And an acid always contains the same ions. Acids contain hydrogen ions, H plus ions. On the contrary, we have alkalis as well. Remember, they're soluble bases, and they have OH minus ions. So what controls the actual pH is the amount of hydrogen ions that that acid has. So for example, if I have a pH of substance 1, I know that the concentration of my hydrogen ions is 1 times 10 to the minus 1. Same as I go down, each time I'm going down by a factor of 10. Okay, each time I'm going 1 factor of 10 less to go up pH by 1. So for example, if I wanted to turn something of a pH 1 into a pH 2, I would add 10 centimeters cubed of water. If I wanted to go from something that's pH 1 to pH 3, well, I would have to go 2 factors of 10, so I would have to add 100 centimeters cubed of water, and that would change my substance from pH 1 to pH 3. Now we say something that is a strong acid, something that contains a lot of hydrogen ions, we can say that that is fully dissociated. What that means is when you add that acid into water, then what happens is the ions separate. So HCl, solid, and I add it to some water, I end up with H plus in aqueous, now it's in water, and Cl minus. And I've got an arrow just going in one direction. However, if I have a weak acid, what happens is I get what's called partial dissociation. And what that means is the reaction is reversible. So you have less amounts of hydrogen ions in that solution. So let's have a look at ethanoic acid here, which is known as a weak acid. And when I add that to water, what happens is I make CH3COO minus, which would be an aqueous, and I'll make my H plus, which would be aqueous, but it's reversible. And this means that there's a lower concentration of hydrogen ions in my solution, and that's why it is a weak acid. But also remember, with weak acids and strong acids, you can always change their pH by changing the concentration of hydrogen ions by diluting your solution. You can have a strong acid that is highly dilute and therefore has a much higher pH than a weak acid as well. So just remember that. The next bit of this video is going to focus on something called electrolysis. And what we use electrolysis to do is it separates ionic compounds using electricity. So do you remember how earlier in the video we were looking at extracting metals using carbon? Well, what happens when that metal is more reactive than carbon? Well, I can't use carbon to do a displacement reaction. So what I need to do instead is use this technique called electrolysis. Now, the first thing you need to know about electrolysis is you first need to make your ions be able to move. And there's two ways of doing this. You can either make it molten, which means heat it to a high temperature so it turns into a liquid, or you can add water and make an aqueous solution. We're going to first focus on a molten solution. So here I'm going to have molten potassium bromide. So that would mean that my electrolyte is potassium bromide. Now, if I have a look at my experimental setup here, I have two what are called electrodes, and these are often made out of graphite. The reason why they are made out of graphite is due to the fact that graphite is very unreactive, and also because it conducts electricity really well. Remember from structure and bonding, it only has 3 bonds per carbon. So it therefore has delocalized electrons. So the next thing we need to know is the name of my two electrodes, and we have two. So this one here is my positive electrode because it's connected to the positive terminal of my battery, and here I have my negative electrode because it's connected to the negative terminal of my battery. So my negative electrode is called my cathode, and the positive electrode is known as an anode. Now, one way to remember this is using the mnemonic panic. Positive anode, negative is cathode. I know some people don't like that because it doesn't work when you've got the anions and cations. It can be the other way around, but that's the way I tell my students, and they seem to remember it pretty well. So, like I was saying earlier, we have our electrolyte, which is potassium bromide. Now, electrolysis, a key thing to remember is that opposites attract. So if I have my potassium bromide and it was solid at the start and I made my ions be able to move by turning it into molten, so it's liquid. Potassium, which is a +1 ion, and I also have my bromide ion as well, which is now also in the liquid state, so they can now move around. And it's really important to know that opposites attract. So my positive potassium ions are going to travel towards the cathode, and my negative bromide ions, which are in the solution, are going to travel towards my anode. But what goes on at these electrodes? Well, to see that, I need to have what's called half equations. So let's have a look at what's going on at the cathode. So my potassium ions arrive at my cathode and they become potassium atoms. So it goes from K +1 to K. Now, how does this happen? Well, to go from a positive ion to a neutral atom, you need to gain electrons, and this is only going to gain 1 electron, and it's going to go from being in that liquid state to now being solid potassium. And what's going to go on at my anode? Well, I've got my Br minus, and it's going to become bromine. Now, remember that bromine is diatomic, so you're going to need 2 bromide ions each time, and for this to happen, it's going to give up 2 electrons to go from 2Br-1 to Br2. And you could probably see this happening as bromide would probably come off as a brown liquid. So you should probably hopefully see a brown liquid being formed at the anode. And at the cathode, remember we made potassium, so you're going to see a shiny metal being formed. Now, I did say that we can also carry out our electrolysis with aqueous solutions. It doesn't have to be molten. I can use water to help my ions be able to move. And when I do this, I introduce 2 extra ions into the mix. I introduce hydrogen ions, which are H+, and I also introduce hydroxide ions, which are OH-. So what's going to happen in my electrolysis is my hydroxide ion is going to be attracted to the negative cathode and travel to it, and my hydroxide is going to travel to my positive anode and be attracted to it as well. So you can make other products in these electrolysis. So there is some rules that you need to know. So at the anode will make either oxygen or your negative ion that's in your electrolyte. And the way to decide what you make is whether a halogen is present. So if you have a halide ion, you will make a halogen. For example, if you had chloride, you would make chlorine. If you had bromide, you would make bromine. Or if you had iodide, you would make iodine in your electrolysis. However, if you have no halide present, what you make instead is you make oxygen. So let's have a look at what is actually going on to make my oxygen. What reaction is taking place at the anode? So what's going on at the anode is I'm having my OH- and it's being turned into oxygen, and also it gives off some water. So let's balance this up. And the way to do that is by putting a 4 here and going from 4 OH-1, and we go to 2 H2O, and also 4 electrons are lost as well. What about the product at the cathode? Well, if I have a unreactive metal, it's less reactive than hydrogen, then you make that metal. Active metal, which is more reactive than hydrogen. And in this scenario, you make hydrogen instead. So just thinking of some examples, maybe if you had sodium or you had potassium or you had even calcium, then in all of these scenarios, you'd make hydrogen. And what actually goes on in the cathode in this example is I go from my hydrogen ions and I go to making hydrogen gas. And the way to do that is by gaining electrons to go from that. And you'll see some fizzing at the electrode because hydrogen, remember, is a gas. Let's have a look at some examples just to make sure that we are solid with this. So if I have, for example, aqueous, potassium, sulfate, what will my two products be? Well, in this electrolysis, I have a highly reactive metal and I don't have a halogen. So my two products will be oxygen and also hydrogen. But what happens if I change up? And this time I've got aqueous, potassium, bromide. Well, this time I've still got that really reactive metal, so this time I'm going to make as my products, I'm still going to make hydrogen because I've got my reactive metal, but this time I've not got a halogen. I have a halogen, that's a better way of saying it, so I'm going to make the halogen as my product. I'm going to make bromine. And I'll just go through one more just so that we've got it. So let's see, aqueous copper sulfate. So here I've got an unreactive metal in copper, so I'm going to make copper as my product. And I'm going to make as my other one, I'm going to make oxygen, and the reason being the fact that sulfate is not a halogen. Let's have a look at a practical application of electrolysis and where we actually use it. So this is the extraction of aluminium, which is done on a huge scale with electrolysis. Now, the first thing to know is aluminium arrives in an ore mainly containing aluminium oxide. And another name for this, and your teachers may have told you this, is bauxite. And this electrolysis works in exactly the same way as all of the other electrolysis do, so the same principles. So I have my two electrodes. I have my positive electrode, which is called obviously my anode, and I have my negative electrode, which is called my cathode. So the first thing I need to do in my electrolysis of aluminium oxide is I need to make it molten. The reason why I can't do an aqueous electrolysis on aluminium oxide is because of the fact aluminium is more reactive than hydrogen, so you'd end up making hydrogen if you did a molten electrolysis. So to make it molten, it requires lots of energy. So the way to mitigate this, to make it a little bit better for the environment, is we add a substance called cryolite. And cryolite is what makes the aluminium oxide a mixture, and it lowers the melting point of the aluminium oxide, so less energy is needed, making it more economically viable and better for the environment as well. Now, another problem with this electrolysis and things that they have to tackle on an industrial scale is the fact that at the anode, the product is oxygen. And because oxygen's being made and these electrodes are made out of graphite, this means that the anodes constantly need replacing because they're made of carbon by being graphite, and this means that they burn away because the carbon reacts with the oxygen making CO2, and this means that they just need constant replacement basically. And looking at what's actually going on at the anode then, so I have my oxide ions and they're becoming oxygen. Just like that. So you'd see a gas being given off. It was in its liquid state, wasn't it? And now we're going to see a gas being given off. And then what's actually going on at my other electrode, my cathode, and I can actually see down here that I'm making aluminium. I did it in a different colour to show molten aluminium being made, and what actually goes on is that gets sifted out through a gap to separate the aluminium from the aluminium oxide mix. And all that goes on at this electrode is my aluminium ions go to aluminium atoms, and the way to do that is by adding 3 electrons, and I go from my aluminium, which was liquid state, to aluminium now, which is in its solid state. Now, I really hope you have enjoyed today's video. I'm going to start making some more GCSE videos again on my channel, so remember, if you do like it, drop the video a like and please subscribe to the channel.